Welcome students to this video, and in this video we are going to talk about linear transformations. So what is the linear transformation? Essentially what we are doing is we are starting out with two vector spaces. Okay, so let x and y are two vector spaces, y are two vector space, and we are going to define a map okay, and let's just call it a map A. Okay, A from x to y. So this is called a linear map. If L of A of x1 plus x2 equals to A times x1 plus A times x2, right? So this should hold for all x1 and x2 in X, of course, and also we need this A times C of x is nothing but C times A of x. Okay, again this should hold for all x in capital X and C is in R, whatever the field you are choosing. So for us this is R. Clear? So you see, we often write, so essentially what happens is, see, we in this course we are always going to write Ax. Okay, so this is essentially nothing but A acting at the element x. Okay, so this is a small notation. Let me just put it this way. Okay, we are going to write as Ax. Okay, of course you can see that if x and x1 and x2 is 0, what we have is A of x. So let's say note that if x1 and x2 is 0, okay, then you can see that A times 0 equals to 2 times A acting at 0. So which will give you A0 equals to 0, right? And this 0 is the 0 element of x. Okay, so this 0 is a 0 element of A is from x to y. So this is 0 element of x, this is 0 element of y. Okay, now so once that is clear, you see what happens is basically why we are interested in linear transformation, because we are going to work with a lot of matrices. Okay, and in this case what is happening is this: a linear transformation is basically nothing but matrices. Okay, so how do you put it? You see what happens is a linear transformation. So let me put it as a remark. Let's say remark that at a linear transformation A from x to y, okay, is completely determined. So you can actually exactly know what it does, okay, by completely determined by its action on the basis, on any basis, right? Any basis. So what do I mean by this? What I mean is, let's say that you start with a basis, let's say x1 xn be the basis of A, be the basis of x. Okay, then you see any x in X can be written as x is nothing but sum I equals to 1 to n. Let's say it is n dimensional, so ci xi. Okay, we can write it like this, right? And if we look at the action of A times x, okay, what it will be is A times summation ci xi I equals to 1 to n. And since this is linear, because from the second property, combining the first and the second property, we know that you can actually write it as summation I equals to 1 to n ci A of xi, right? We can write it like this. So you see what is happening is this, that the linearity of A will allow us to compute A of x, okay, from the vectors ax1, x2, xn. Okay, so this is what we want to say, that it is completely determined by the action of its basis. Okay, and you see another small remark A, B, let me put it this way, small remark B, that the linear transformations from x to x, let's say, transformations from x to x, transformations from x to x, we will call that are called linear operators on x. Okay, are called linear operators on x. I hope this is clear. Operators on x. This is just a name, nothing special. Okay, so you see what is happening is this. Okay, so now what is happening is this. So basically we want to find out some properties. Okay, what are the properties that can be satisfied by a linear operator. So let's look at a small theorem. So let's say that a linear operator, let's say you are given a linear operator on a finite dimensional vector space x, right? So a linear operator, let's say, and let's just call it a L now, of operator L. Operator, you remember, it is from x to x. Okay, a linear operator, let's say L, defined from x to x. Okay, is 1 1. So when can we say it is 1 1? This is a if and only if condition. If and only if the range of A. Okay, if the range of A is x. So basically it is all of x. Okay, so if the range is all of x, then basically you have that the linear operator A is 1 1, right? So what is the proof of this? Let's look at the proof of this thing. Very simple proof, but let's look at the proof. So let's say we start with a basis, right, of x. Xn be the basis of x, Okay, now the linearity, since A is linear, right? Okay, what does it mean? It means that the range of A, the range of A, let's just write it like this. This is the range of A. Okay, how can you write the range of A? So this is nothing but the span of this element, right? You see, this can be written as the span of ax1, axn, right? The span of this is called the span, this, or we write it as the span of these vectors ax1, axn. Okay, you remember, because you see from the last slide you can see that any ax can be written like this, right? So basically what happens is, if you start with the element of range of A, which is ax, then you can write it as a linear combination of axis, right? So you can write it like this. Now you see that you can easily see that R of A, okay, is x, if and only if, what is the condition? If and only if A of x1, A of x2, A of xn, this set, okay, this is independent. If and only if the set, so let's write it as ax1, axn, this is independent. Clear? This you can easily see that R of A has to be x if and only if Q is independent. Okay, so basically we have to show that A is 1 1. Okay, so basically sorry, I am writing A here, so let's write it as A, because I started our linear operator as A, right? So we should write it as A. Okay, so we should do it like this. Okay, so range of A is x if and only if this is independent, right? Okay, so we have to show, okay, that this can happen if and only if A is 1 1. So how do you show that? So let's say A is 1 to 1. Okay, if that is the case, and let's say that summation Ci axi is 0. Okay, I equals to 1 to n. So basically it is independent. I am assuming this thing. Okay, then what is happening is that will imply A of summation Ci xi is going to be 0, right? Because of the linearity, and then one can write down summation of Ci xi has to be equals to 0, right? And then since so A is 1 1, right? So basically you see, if summation, so this is 1 to n, if summation Ci xi is equals to 0, that will actually imply that C1 has to be equals to C2, that should be equals to 0, right? Why? Because since A is 1 1 and A of 0 is equals to 0, so it will give you that summation Ci xi has to be 0. Okay, and then you always have that ci's are 0 because x1, x2, xn's are the basis of x. Okay, so that is there. So that will actually imply that if ci's are 0, so summation ci axi is 0 and ci's are 0, that will imply that the set ax1, axn, this set is linearly independent, right? Is linearly independent. Linearly independent. Okay, now the thing is, let's look at the converse. Okay, so what happens if the set is linearly independent and a of summation ci xi is 0? Okay, so let's look at the converse now. Converse. So let's say that the set a of x1, a of x1, a of xn, this set. Okay, let's say this set is independent, linearly independent. That is linearly independent. Linearly independent. Okay, and a of summation ci xi is 0. I am not writing I equals to 1 to n, that is implied there. Okay, so that will actually imply that summation ci axi is 0. This is very easy. Of course, because of the linearity we can write it, and that will imply that ci's will be 0 for all I, right? I equals to 1 to n. This is true because a of x1, x2, xn, I have assumed that this is going to be linearly independent, right? So this is true. So this will imply that a of x equals to 0 only if x equals to 0. Okay, so you see, now let's say that if a of x equals to a of y. Okay, so if now ax equals to ay, okay, that will imply a of x minus y is going to be 0, linearity, and that will imply x has to be equals to y. Okay, and that will imply that a is 1 1. A is 1 1. So basically, you see, you started with the linearly independent set, you showed it is 1 1, and the converse also. So we can actually say that the linear operator A is 1 1 if and only the range of A is going to be whole of x. Okay, now we need some definitions. Let's do some definitions here. Definitions. So the first definition which you are going to do is this. You see, we are going to write down L of xy. This is the notation which we are going to use. L of xy. This is the set of all linear transformations. Set of all linear transformations. Linear transformations. Transformations or linear maps, whatever you want to call it. Linear transformations from x to y. And give from x to y, and of course we are assuming x and y are vector space x to y. Clear? And you see, if there is a linear map operator on x, it means that we just write L of xy. And L of xx, so basically a linear operator on x, we just write it as L of x. Clear? Okay, so this is just a notation which you are going to use, right? Okay, now the thing is this, what we are going to do is we are going to define a very important notion. So we are going to define the norm, right? So let's say for a linear map A from Rn to Rm, Rn to Rm. Clear? What happens is we define the norm A of A, okay? And how do we define it? We define it to be the we define the norm as norm of A, supremum of this set Ax. Okay, so basically we are looking at where A is acting. So basically we are choosing A from this unit ball, less than equal 1. Okay, and we are looking at how A is acting on that every element of that ball. Okay, and we take the supremum of such a set. Okay, right. So how do you know such a supremum exists? You see, A is a linear map from Rn to Rm. We know the linear maps, so we know that linear maps are going to be continuous on finite dimensional spaces, right? Okay, and since it is a continuous function and this set is a compact set, we know that the maximum or supremum, whatever you want to call it, in this case maximum, but let's just stick with supremum here, but the supremum exists, okay, and that we are going to call it as a norm of A. Okay, right, and we can also observe, okay, observe that mod of X, okay, sorry, one thing, I have to put a mod here, otherwise the norm won't be defined. Okay, so it is the supremum of mod X. Okay, so you have to observe the mod of X. So A of X, okay, sorry, it's mod, what am I saying? It's not mod. A of X is in Rm, right? So this is M and this, okay, so this is Rn, so the norm in Rn, this is what we are taking, and this is the norm in Rn. Okay, let me put it this way. Now Ax is a norm in Rm, okay, and this is always dominated by norm of A. What is this norm? This norm is defined on L Rn Rm, okay, and times the n norm of X, okay, because this is the supremum, right? You see, we are looking at supremum of X, that is, we are defining it as the norm of A. So basically norm of X can always be dominated by norm of A times norm of X. Okay, right. I hope you can see why this is true. Okay, so please check this part, just keep this in mind, that any element Y, okay, let's say you are starting with any element in Y in Rn, then Y by norm of Y, okay, n norm, Rn norm, that is always 1. Okay, now you can use this fact to prove something like this. So this is very easy to show, so please do that. Okay, right. So now there are two theorems which I need to know, proof theorems. So the first theorem is this: if linear transformation from Rn to Rm, A is a linear transformation from Rn to Rm, okay, then the norm of A is finite, okay, and A is uniformly continuous, okay, uniformly continuous. The continuity part is very easy, okay, that you can of course prove, but it's not only continuous, it is more than that, it is uniformly continuous. Now B, okay, so this is a small another, let me put a small note here, check that A, which is a linear map from Rn to Rm, is continuous. So maybe you can, of course, there is nothing special to check because we are going to do it here itself. But so basically, it is not only continuous; this is uniformly continuous. Okay. So and of course, what we have is this. So if, let's say, if A and B, we are choosing two elements from L Rn to Rm. Okay. So two linearly, linear transformation from Rn to Rm, and you are choosing a C from a scalar, which is R in our case, then you can actually show that norm of A plus B, so it satisfies the triangle inequality, less than norm of A plus norm of B. Okay, and mod of C times A, okay, is equals to mod C norm A. Clear? Okay, so this is there, and of course, what another important criteria which we need to do is this. Let's say if A is a linear map from Rn to Rm and B is a linear map from Rn to Rm, Rm to Rk, let's say, yes, Rk, okay, then we can actually define, of course, BA, right, and we can define the norm of BA. Then BA will be dominated by norm of B times norm of A. Okay, these properties are very important. We are going to use these properties when we define something called a matrix exponential. So you should know these things for a fact. Okay, so let's look at the proof of this. Proof. So the first thing is this: you have to show that the norm of A is finite and A is uniformly continuous, right? That is what we need to show. Okay, so what we are going to do is we are going to start with the standard basis of Rn. So E1, E2, En, let's say, be the standard basis of Rn. Be the standard basis of Rn. Standard basis of Rn. Okay, basis of Rn. And let's start with an element x, so we can write it as summation xi ei. Okay, I equals to 1 to n, right? So once we do that, and we also choose this x in such a way that norm x is less than equal 1. This norm is in, of course, in Rn. So the norm, Rn norm. Now you see why we are choosing it, because you see we have to show that norm of A is finite, right? And how is norm of A chosen? You see, we are not looking at the whole of Rn, but only in the unit ball, which is less than equal 1. Norm x is less than equal 1, so I am choosing my x accordingly. Clear? Once we do that, this will actually imply, so you see, this will actually imply that the modulus of each xi, okay, sorry, each xi is, they are less than equal 1. Okay, this of course you can see, right? This is very easy to see for I equals to 1 to n. Clear? Okay, so once that is true, then one can write down, you see, A of x. How does A of x looks like? It looks like summation Ci A of ei, right? That is how it looks like, linearity 1 to n. And then these can always be dominated by summation mod Ci mod A of ei. Okay, how am I writing it? I am using this property. You see, observe that Ax is less than equal norm x times norm of A times mod of x. Okay, so I am using this property here. Okay, and of course with the triangle inequality. So this is I equals to, sorry, this is I equals to 1 to n. Okay, now okay, now what am I? So A of x is this, which is dominated by mod Ci times norm A. Clear? So this is true. Now how can we do it? Okay, so this is again dominated by summation mod A ei, right? Why? Because you see all this, sorry, I am writing Ci here. This is why I couldn't find out what is happening. So xi times ei. Okay, so since each xi is less than equal 1, so we have this is less than equal A of ei. Okay, one thing, I made a mistake here. So basically this is just a scalar times this vector, right? So we are using this triangle inequality here. Okay, right? So we are not using this fact, we are not using this fact, but we are just using the triangle inequality. Sorry for the mistake. Right now, so once you have this, then you see what we have is therefore norm of A, which is nothing but the supremum of this for mod x, norm x less than 1, okay, is always dominated by summation I equals to 1 to n mod of A ei, norm of A ei. Okay, which is dominated by which is finite. Clear? So that is clear, because this is just n numbers, which is basically the sum of n numbers, which is going to be finite. So norm of A is always going to be finite. Okay, and you see, and A of x, okay, minus A of y if we do. So basically I have to show uniform continuity, right? For that, A of x minus A of y, you can actually write it as norm of A times mod of x minus, norm of x minus y. Okay, this is where this inequality I am using. So mod of ax is less than equal norm of a norm of x. Okay, so this is what we are using here. So this is true if for all xy in Rn, right? For all xy in Rn. So if this is true, then you see we can of course see that since this is true, A is uniformly continuous. Clear? Okay, now what about the second property? What is it? Norm of the norm of A plus B is dominated by norm of A plus norm of B. Okay, So the second property C, sorry B. Okay, so first of all I am starting out with the norm of B. So the any element of a plus b. So a plus b times x. I want to see what is the action of a plus b on a arbitrary element x. Okay, so this is nothing but ax plus bx. Ax plus bx. Yes, and by triangle inequality I can write it as ax plus bx. I hope what I am doing is clear to you. I am using triangle inequality here. Okay. See, a and b is from Rn to Rm. So ax plus bx, this is in Rm. You see, this vector is in Rm. Clear? Since this vector is in Rm, I can use the triangle inequality in Rm. Clear? That is what I am doing. Okay. So if this is true, then you see this is again dominated by, you can see this inequality that norm of ax is dominated by norm of a times norm of x, right? So this is dominated by norm of a plus norm of b times norm of x. Clear? Okay, once this is true, of course you can take the supremum now and you can see that the result follows. Clear? Okay, so taking supremum, the result follows. Supremum, the result follows. Okay, and the second part is I want to, so please check that this property, that's mod CA, norm CA is equals to mod C norm A. Okay, so CA equals to mod C norm A. I want you to check this part. Okay, so please check this part. This is accordingly done in the exact same way. So if you want to look at norm of CA, you start with CA acting at an element A, and then you do accordingly. You use triangle inequality or whatever appropriate inequality is there, you can actually get it. Okay, now let's look at the third property. What do you have? See, the third property is this, that norm of BA is dominated by norm of B times norm of A. Okay, so again we want to look at what BA does to an arbitrary element x. Okay, the norm of that. So this is nothing but B acting at x, right? That's the definition. And this is we can write it like this, right? Ax, you see, Ax is an element here. Ax is an element of Rn. B acting at the element of Rm from Rk, right? Okay, so you see, this is the element of Rm. Okay, and the whole element is in Rk. So this is the norm in K. Okay, so the norm in K. Okay, so now we can use this inequality again. Norm of Ax is dominated by norm of A times norm of x. Okay, so this is dominated by norm of B times norm of Ax. Clear? And that is dominated by norm of B, and norm of Ax is again dominated by norm of A times norm of x. Okay, let us write it down like this. Okay, see, the thing is, once that is done, now you can take the supremum. Now taking supremums, you can find out the result. Taking supremum, so we have one has that the norm of BA is dominated by norm of B times norm of A. Clear? So this is true. Okay, now so this is more or less what we need to know on the linear transformations. Okay, with this I am going to end this particular video.